Nuclear reactions and half-life in a nutshell. So let's get started. So nuclear reactions, there are two types you need to be aware of. One is fusion. There's a deuterium and tritium, basically two different isotopes of hydrogen. You can see both have one proton. It says one neutron, it says two. It's a difference. So when two things come together and produce something new, which is bigger, obviously, you have what's called fusion. Fusion is a really great process because it has zero waste, whereas nuclear radiation and fission, which we're going to talk about in a few minutes, has some byproducts that can be really harmful. Fusion is really good because this byproduct is helium and neutron. That's if you do fusion with hydrogen molecules, which is what occurs in sun and stars. That's how they generate their energy. The other byproduct is a neutron, which can then be used to start another nuclear reaction, another fusion reaction. So there's a lot of benefits to fusion, but unfortunately there's some big issues with fusion. One, you're forcing two positively charged nuclei to get together. It's kind of like putting two magnets together that are the same polarity. They'll repel each other. They don't want to get near each other. Same dynamic here. So in order to accomplish it, you need a temperature in excess of 100 million degrees Celsius, which is extremely high. And for us to simulate it on Earth, and we're going to need magnetic fields. It's a very complicated process, and there's the promise that if we can accomplish it, then we not only eliminate our dependence on oil and other carbon-based fuels, but we also will have an infinite source of energy that is basically environmental friendly, which would be awesome. And plus, you're producing more helium. We do have helium shortages like crazy. If you've ever gone to buy a helium tank, you know what I'm talking about. All right, fission on the other hand, opposite. Atomic bomb nuclear reactors undergo fission. Neutron activates the reaction. You shoot it at the uranium atom. This is for nuclear bombs. And for nuclear power plants, same principle, not necessarily the same element being bombarded, but neutron hits the atom, causes it to undergo chain reaction where it produces two other atoms, more neutrons. Neutrons go on to hit other atoms and keeps on going and going. And in the process, you're generating large quantities of energy and byproducts. The problem with fission is that you can have, and you will have, nuclear waste. These are byproducts of nuclear reaction, which unfortunately you cannot really get rid of safely. You would have to store. And when you store something, eventually you're going to be exposed to some sort of problem years later. Primary location for storage right now is New Mexico. They have mines down there, and they locate the waste down there because we do have nuclear power plants in the U.S. Most people aren't aware. We have a large number of them, actually. I think it's about 38 throughout the U.S. And all that nuclear waste has to get stored somewhere. You can't just park it at the nuclear facility. You have to put it somewhere else, somewhere deep underground that hopefully eliminates it being an issue for exposure for other people as they get near it, or for us. A large amount of energy is produced like fusion, but have nuclear waste as well, and that's the problem. Producing radioactive isotopes. So now that we've talked about fission and fusion, let's talk about how do you produce radioactive isotopes, some of which are used for health purposes, and that's the big reason we care about this. So here you have a helium atom, or an alpha particle, being shot at a stable nucleus of boron, and you produce this radioactive isotope of nitrogen. You can see the ratio of protons and neutrons. There's exactly 7 protons, but 6 neutrons, so it's not 1-to-1. That's why you can say it's radioactive. You'll just get a neutron as a result of it. So the reason we produce these kind of things is that we're trying to use it for a purpose, and typically it's for health purposes. That's one of the more common uses, and there's a whole host of different things you can do with it for cancer treatment or for identifying possible cancer and other health issues. All right, half-life. Time required for half of the atoms in any given quantity of a radioactive isotope to decay. You've probably heard of half-life, whether it's via a video game or some other source. It's basically, if I start with 10 grams of something, how long does it take me to get to 5 grams? That's what half-life is in a nutshell. So this is called your half-life, and let's say this takes 1 day. Then your half-life is 1 day. That's how it works. So what would happen in another day? Well, you go half again, right? It's actually 2 days if you want to be accurate. And then 3 days, you go half of this and you keep on going. That's the premise of half-life. You just take the starting quantity and you keep on halving it for how many times you need to. For most nuclear particles, especially the ones that are deadly. It takes about 8 half-lives for it to become safe. It's a general rule. So you could also go at 100% as your starting point. So after 1 day, you get to 50%, which is 5 grams. After day 2, we're left with 25%, and then you go to 12.5%. It keeps on going half each time. This will be day 3. You keep on going. That's the premise of Half-Life. Each half-life, you have the amount you're starting with. Can be used to age materials in the case of carbon-14. So let's talk about half-life calculation. So once again, all you're doing each half-life, so this is one half-life, this is another half-life, you just half the amount. So how many half-lives does it undergo? Well, and after one half-life, you're left with 20 grams, right? Then after another half-life, you're left with 10 grams because it underwent 2 half-lives. This is the first half-life, right? And this is the second half-life. That's all half-life is. That's how you do it. Whether you do percentages, you start with 100 and keep on halving that number, 100, 50, just write it down so you can see what I'm talking about. 100, 50%, 25% of the original amount, 12.5% of the original amount, 6.25%, 3.125, and you could go on and on and on. So that's what half-life is. Each time you're going to go half-life, you decrease the quantity by half. So here's a curve that shows that. So you're starting with 20 grams of this by the looks of it. So after one half-life, and for those wondering, or if you want to really think about it, what is the half-life of this? Well, the amount of time it took to get to half whatever you started is against your half-life. So you start with 20, half of that is 10, so 8 days is your half-life. So every 8 days, the quantity of chemicals decreased by half. That's what it means. So after one half-life, you're at 8. After after one half-life, you're left with 10. After 2 half-lives, you're left with 5, 3, you're left with 2.5, and this is going to be 1.25 and 0.625, and it keeps on halving. So that's the principle of half-life. And that's what this curve is showing you. For each half-life, you're going half whatever you started. So here's some isotopes and their uses. You can see naturally occurring radioactive carbon, potassium, radium. These are the radioisotopes. These are the ones we artificially typically produce, or the radioactive isotopes, the ones that are found naturally in nature as well. It's not just necessarily us producing all of them. These are the medical ones, carbon-11. You can see half-life, fluoride, iodine, iron. Here's the interesting thing. Look at the time frame for these. You see how this is hours, minutes, days. This is the longest at 46 days for iron. Second would be 28. But most of these are really short, right? They're less than a day, not including these 1, 2, 3, 4 that are not days. The rest are less than a day. They're really short, and that's really important because you don't want something inside your body that takes a long time to degrade, because that can basically shoot radiation at you the whole time, right? Remember, you're internally digesting this stuff. So if it's inside your body, we're talking about how alpha decay and beta decay, they're not deadly from the outside, but they're really deadly on the inside. So you technically are radioactive when you consume these. So you can actually cause radiation to other people around you. And that's why when you undergo certain types of treatments, they may make you stay in the hospital in a location that is safe from radiation from around. So it either has really thick concrete or lead on the outside of it, so that basically you do not expose others to your radiation because you are completely radioactive at that point. Whereas the ones up here, you can see they're pretty short half-lives, right? Right there. These are pretty long half-lives, excuse me. You can see years. This is stuff you don't want in your body, obviously, right? Because it's not going to work. Whereas these, you're okay with it compared to these anyways, at least for the ones that have half-lives less than a day. And you can see what kinds of radiation. This is beta, gamma, positron. So not as bad for you because the fact that it degrades, and after 8 half-lives is safe. So that means for like the one that has 6 hours down here, after 48 hours, this is probably going to be safe. Doesn't mean it's extremely deadly for you at the amount they put it, because they're going to put really small quantities, but still, after 8 half-lives, something's completely safe, so it's no longer an issue. So those nuclear medicine to be very short. All right, so here's some radioactive dating possibilities. So you've probably heard of radioactive dating, carbon-14, if you took history class that dealt with that, how you age objects are extremely old. So that's carbon-14 is used for ranges of 500 to 50,000 years. It has to be carbon-based for carbon dating to work. If it doesn't have carbon, it's not going to work. So what about things that are wines? Well, you could date them with hydrogen-3 or tritium. Skeletal remains, you could use lead. Kind of weird. You analyze based on lead, but yeah, you do have some lead in your body. Rock and earths use uranium, meteorites, uranium. So different types of material help age different things. And what they do basically is they know how much should be in the object, and then based on the quantity that's in there, they could extrapolate and figure out how old it is. And that's the way the concept works, using the concept of half-life. Question related to half-life now that we have a basic understanding of it. So right now you have iodine-123, and the half-life is 13 hours. So this is when we consider the half-life. So we're going to do a little table to help organize our information to make it a little easier. We'll call this time, half-life, and amount. Now, for amount, you could do percentages. So for example, after one, so this is 0, this is 0. So after no half-lives, you have 100% of the quantity of the chemical. After one half-life, you get half, so that's 50%. After 2 half-lives, you get 25%. After 3 half-lives, I'll put the percent symbol so you can see how this is working. After 3 half-lives, you get 12.5%. And these are always constants, just to be very clear on this. This is something you could always apply to kind of organize your information. So you do time, which is 0 to, the most you're going to see is 6. So let's go up to 6 just for fun. So this would be 3.125, and this will be 1.625, I believe. Okay, these are all percentages. Now that's if you don't have quantities of chemicals. So you have 64 milligrams, of 123 is left after 26 hours. So instead of doing percentages here, I'm gonna go actual amount. So after one half-life, how much do you have? 32. After another half-life, remember, all I'm doing is just halving the quantity. It's nothing complicated. So we have 8, we have 4, we have 2, we have 1. So the half-life is 13 hours. So where do I put that information? Right here, where it says half-life. So that's where it goes. What if I wasn't given that? Well, whatever number you're given, let's say after 3 half-lives, the time is da-da-da, you put it there. But for this context of this question, we want to know how much is at 26 hours. Well, we know that this thing takes 13 hours. So how do we figure 26 hours? Well, the way it works, the way the system works, you multiply this times the time, the half-life times time, to get the value here. So that's 26 hours. So if I'm trying to go here, 13 times 3, that's going to be 39 hours. For those that can kind of see a pattern real quick, just adding 13 each time, nothing really fancy here. So this would be 4 half-lives, would be 52. Then you can keep on going down from there. So the question is, how much of a sample is left after 26 hours? After 26 hours, that's basically 25% left, right? Which we know is 16 milligrams. So that's how you figure it out. You set up a table, you organize it. Vast majority of the time, you're not going to go put past 4 half-lives, so it's not going to be that complicated. But if it is, the most you're going to see is 6, and that's even rare. So that's how you interpret half-life, and that's some basics of nuclear radiation, how it's used.